Okay, we're going to explore a little bit what an inverse trig function it is, where it comes from, and how to use it. So I wanted to take a slightly different approach than what you might just read straight textbook definitions and kind of show where it comes from and how you have probably already seen an inverse trig function. So let's take a look at this example. I'm not asking to solve the entire right triangle, just find theta. Okay, so finding theta. The two sides that are given, now we of course can use Pythag to find this adjacent side, right? But the two sides that are given is opposite and hypotenuse. And by SOHCAHTOA, I know then we would use sine of that angle, theta, equals opposite over hypotenuse. Now, this should look familiar. Sine root 3 over 2 is one of the special angles on a unit circle. So without going any further, you should recognize this as 60 degrees or pi over 3, right? And on that note, more often than not, we will be using radians. I left a little room here because I want to talk about it a bit. Like, you may get things that are not in the unit circle, so it would require a calculator. Up to this point, all we have really talked about, is like, all right, if you need the angle, use your calculator, do sine inverse. But your calculator will not spit out pi over 3, right? It'll give you that decimal answer, 1 point, whatever it is, if you're in radians. So that's okay. Sometimes it's just not a special angle, right? But we still need to know that value. So how this is written is that we do sine inverse on both sides. Okay, whatever, if you have an equation, as long as you do the same operation on both sides of the equal sign, then that's acceptable. And the reason we do this sine inverse is because an inverse function, sine inverse and sine, would cancel, and therefore I would only have theta on the left. Now sine inverse of root 3 over 2 just means what angle, right? What angle gives a sine value of root 3 over 2. And we know that's pi over 3, or again 60 degrees. But why wouldn't we answer this as, right, all students take calculus. I know sine has two of the same values, so the second value is over here in quadrant 2. So why wouldn't we use this angle as our answer? Now, in the picture that I have drawn, sure, it's a right angle, right? So I know theta has to be less than 90 degrees, less than pi over 2. But what if the problem ultimately just started as this? If I said find theta, I didn't draw a triangle, and I said sine theta equals root 3 over 2. I mean, are you wrong if you told me that theta is the angle in quadrant 2, which would be, what, 120 or 2 pi over 3? Sorry, I had to think about that for a second. So if I just gave you that problem, sine theta equals root 3 over 2, like, what is wrong with telling me theta is 2 pi over 3 or 120 degrees? So that's where we have to really investigate, what does it mean to be sine inverse? What does that function look like? What does that represent? If I had asked this question differently, like if I said what angles would yield this ratio, this ratio here, then you could answer both. It is pi over 3 and 2 pi over 3. That is true. But in inverse trig function, we are restricted, our domain is restricted. So let's take a look at why. Recall that an inverse function the original function has to be one-to-one. So what do I mean by that? Like say a parabola, we could not do an inverse function here because the original function is not one-to-one, which means it fails the horizontal line test, which ultimately means there are two different x values that yield the same y value. However, if we restricted that domain, okay, if I told you that, all right, we're looking at x squared, but only where x is greater or equal to 0, I now can find that inverse, right? If I told you x squared where x is greater or equal to 0 only, that inverse is this function. Maybe I should have did it in blue, that's okay. So I should have used function notation, that's right. F of x is x squared where x is greater or equal to 0. The inverse function is the square root of x. And again, x is greater than 0, y is greater than 0 too for that case. But last, remember an inverse function reflects across this line y equals x. Okay, so a little bit of quick background, and why do we need that? Because think of the function sine, right? 0 to 2 pi, it's periodic, and the range is -1 to 1, right? And it does this. Already I could see that is not 1 to 1. So how do I make this 1 to 1? How do I restrict the domain? Well, we have to look backwards. So drawing a few more here, there's -pi, -pi over 2. We have to look in the negative axes here, where x is negative. Whoops, that's should be there, that's okay. It really wouldn't matter. So the shortest way to restrict this domain and create it 1 to 1 is by only looking there. Right? If I looked beyond pi over 2, I could see it starts to fail this horizontal line test. So we're restricting the domain from -pi over 2 to pi over 2. And therefore, like in the quadrants of the unit circle, all students take calculus, quadrant 2 is out, right? -pi over 2 to pi over 2 is restricted from here to here. So for sine inverse, we only use the negative angles here down to -pi over 2 to pi over 2. Okay, typically we avoid negative angles, that is true, but for the inverse function, right, we don't have a choice. And this is also true for tan inverse. Recall that tangent does this, and there are asymptotes at every multiple of pi over 2. So, well, I'm sorry, pi over 2, and then add pi, right? Every pi, 3 pi over 2, and so forth. Okay, it's periodic, but its period is pi. So, again, tangent, it is not 1 to 1 if we look at the entire function. It fails the horizontal line test. But if we restrict our domain to -pi over 2 to pi over 2, then we're good. Cosine is slightly different. Remember that the graph of cosine actually starts at 1 and ends at 1 out at 2 pi. So at pi it hits -1. Right? This is the graph of cosine. Whoops. Drawn a little too archy there. So if we restrict the domain here from 0 to pi, we now have a one-to-one function. So cosine, if we look at the quadrants of our unit circle, cosine actually goes from 0 to pi here. Okay, so cosine inverse, sorry, the inverse of cosine, right, goes 0 to pi. And it's because that's how we had to restrict it on the graph. All right, couple more things briefly. One is, remember that in inverse, what we do is we change the x with the y, right? Or we change the domain and the range. The domain of the original becomes the range of the inverse, and the range of the original is the domain of the inverse, right? Back and forth. Also, as I said for the x squared, the inverse function will reflect across that line y equals x. Okay, I don't have perfect drawings here, but if we picture a reflection, right, then you could kind of see how the inverse trig function looks. So something like, what do we have? Here, let's see, crosses 0 there, reflecting about that. Oh, that's hard to picture, this graph. Let's see here. Maybe something like that, actually. Okay, check the, don't trust my art skills perfectly here. So I'm going to give up actually on that. You can look at the graphs of the inverses. I think it would be easier to picture it as, let's change x and y, right? So we have, on the original, we have pi over 2, 1, so therefore I'm going to go 1, and then the y is going to be pi over 2. And then 0, 0, I could change that pretty easy. And then we'd have negative pi over 2, negative 1, so now I would have negative 1, negative pi over 2. Again, rough sketches, right? And then kind of eyeballing it here. Goes something like this. Okay, sorry for my failed attempt over there. Anyways, check it out. You can also graph these if you use your graphing calculator or GeoGebra and graph sine inverse of x. Be sure you're in radians. Remember that sine inverse is not equivalent to this not 1 over sine. So also, if your calculator you don't find sine inverse, it might be arc sine.